Hello everyone. Today we will discuss about process scheduling. So as we have discussed in the video of multi-programming versus multitasking, that in multi-programming you have multiple programs in main memory and they only one process runs on a single processor system. So if that process is running and it requests for some IO device, so it will wait for the completion of that IO request, and meanwhile it is waiting, your CPU is idle. So instead of keeping that CPU idle, in case of multi-programming environment, some other processes allocated CPU. So basically the objective of multi-programming is to have some process running all the times to maximize CPU utilization, because you are if one process is waiting for some IO completion or some other event, another process is allocated CPU. So you are maximizing the CPU utilization. But in case of time sharing, every process has a different time quantum, and if that time quantum expires, some other processes allocated the CPU. So basically there the CPU is switching among processes so that the user can interact with each program. I have discussed this topic, multi-programming and multitasking, in detail. So if you want to see that video, you can click on the I button. Okay, so in both the cases, whether it is multi-programming or time sharing, how are you going to decide that which process will be executed next? Since we have different processes in memory, so who will decide this basically? So the process scheduler selects a process from a set of several available processes. Okay, so that is the job of your process scheduler. So, and if it is a single processor system, there will be only one process running at a time. So if there are more than one process, so the rest will have to wait until the CPU is free and can be rescheduled, right? Now, as the process enter the system, they are put into a job queue, which consists of all the processes in the system. And if the process is in main memory and they are ready and they are waiting for CPU, they are kept on a list known as ready queue. So basically this ready queue, which is, as we can see here, is generally stored as a linked list. It has a head pointer and a tail pointer. Head points to your first PCB and the tail points to the last PCB in the list. And each PCB has a next pointer which points to the next PCB in the list. Now suppose a process is executing, that process request for some IO device, let's say disk. So the disk, it will use that disk. Now let's take a proper example. Suppose you have process P1, P2, and suppose there are three processes only in P3. They are in ready queue, let's say, and P1 is allocated CPU. While running, it requests for some IO device, let's say some disk. Now so basically P1 will can access this disk now. Now since P1 is busy with this disk, P2 will be allocated CPU, let's say. Now while P2 is executing, now suppose this P2 also want to access the same disk, but since your disk is already busy with process P1, so this P2 will have to wait. So this P2 now will wait in the queue for this particular device. Okay, and since there are many processes in the system, the disk may be busy with the request of some other process. Like in our case, this disk is busy with the request of this P1 process. So this process P2 will therefore may have to wait for the disk, and the list of processes waiting for this particular for a particular IO device is called as a device queue. Okay, and for each device has its own queue, device queue. Okay, so that is about your ready queue and other device queues. Now let's see the queuing diagram representation of process scheduling. So here your each rectangular box represents a queue and each circle represent some, you can say, resource that serves the queue. Okay, so a new process is initially, as we all know, the process which are ready for execution and they are waiting for CPU are put inside the ready queue. From this ready queue, one process will be picked and it will be allocated CPU. Now while running, suppose that process request for some IO device. Now, since this IO device will have its own IO queue, so it will wait in that particular IO queue. And once waiting, suppose now after waiting for some time, this process will be allocated the particular IO resource. And once the service is the request is completed, then it will go back again to the ready queue. Similarly, suppose while executing it requests now suppose it is a time sharing environment. There, as we all know, that every process has some time quantum. So let's say some process from ready queue is picked and it is allocated CPU, and while running its time quantum expires, so it will go back to the ready queue. Then now the third case could be, let's say this process is executing and it creates a new child process using fork. Now, since it has created a new child process, so it will wait for that child process to complete first. So it will wait for the termination of that child and then again it will go back to the ready queue. Now, let's say the process was executing and the other case can be like the process is executing and some interrupt occurs. So the process will be forcefully removed, removed from the CPU, and as a result of an interrupt, it will be put back into the ready queue. So in the first two cases, the process eventually switches from waiting state to the ready state and is then put back to the ready queue. And a process basically continues this cycle until it terminates. And when it terminates, the it is removed from all the queues and its PCB and resources all are deallocated. So I hope this topic, process scheduling and different queues, are clear to you. And now how a process is picked from ready queue and is allocated a CPU, and how like from job queue they are picked. So for that we have different kind of schedulers, long term, short term and medium term also, that we will discuss in detail in the next video lecture. If you have any queries, please drop them in comment section. Thank you.